That isn't going to work. Let's try this way. There we go. Okay, I'm pretty much done with lecture after today. So I have a few more problems to knock off from 6.7. Okay, so as I said last week and a half or so, we're probably going to finish early. And then you can ask questions. Tomorrow you can ask questions. There's no more new material to go over, of course. Again, please notice the test this week is on Thursday, not Friday. Okay, so I'll finish up the last 3 problems. Well, I say 3 problems, but each problem has 4 parts to it. So it's a little bit longer than that, but hopefully not too much longer. Okay, so question and answer tomorrow, test Thursday. You turn in all of this stuff. 70% requirement, as usual, of turning in the homework in order for me to grade your exam. What's going to happen Friday? Friday, I'll let you ask questions from previous exams. Again, that's the best way to study. Again, I'm not promising you I'll give you all the tests, get your tests back by Friday, although I'm going to try, but I'm not sure I can do it. I will make the video for you so you can at least look at the video and grade yourself sort of in preparation for the final, since our final is the very first hour of Monday. Okay, so Friday you can come in with questions from previous exams. That's the best way to do it. And so you can ask me questions from any of the exams. And then Monday is our final exam right away. No homework needs to be turned in. Please notice the starting time is 8:10. So again, on Canvas announcements, I'll send the exam, final exam, maybe like 8:01 or 8:02, something like that. And then as usual, you join. You don't have to turn any homework for that. Use all the previous cheat sheets, or if you need to make them again, that's okay. And then by 10:40 Monday, we're all done. Again, I do have office hours. I sent you a Canvas announcement about my office hours. I know it doesn't really make a whole lot of sense to have office hours after the final, but I'm required legally to tell you, so I told you. So there it is, okay? All right, so I'm going to knock off the last few problems from 6-7, and we'll probably be done early. Then I'll let you ask questions, and if there are no more questions, we're done. So tomorrow, come up with any questions from anything in Chapter 6. And then Friday, your quote-unquote homework is to come up with questions from previous exams. Okay, so we're finishing very rapidly. All right, so my game plan was simply just to do the last problems, which were 15, 17, and 19, and then that's pretty much about it. Okay, so think about any questions you might want to ask, and if there aren't any, then we'll just end early. Okay, so 15, the theme that we had again was you see a lot of sines and cosines, so you try to force there to be a sine squared plus cosine squared equals 1. Okay, and it would end up being one of the conic sections that we've seen before, hopefully. So 15a, x is sine t, y is cosine t. So all I do is square both sides here, x squared equals sine squared t. Square both sides here, y squared equals cosine squared t. Then just add them up. X squared plus y squared is sine squared t plus cosine squared t, and that's equal to 1. Okay, so whenever you see a sine and a cosine together, you try to force the equation to be sine squared plus cosine squared, because that's just going to be 1. Then you eliminate the t. So x squared plus y squared equals 1. That's our familiar unit circle. Okay, but which way does it go as t increases? So I just make myself a little mini chart here. I went from 0 to pi over 2, let's say. So t equals 0. So sine of 0 is 0. Cosine of 0 is 1. So we start at 0, 1 at the top. And then I plug in pi over 2. So sine of pi over 2 is 1. Cosine of pi over 2 is 0. So I go from 0, 1 to 1, 0. So my arrow is going this way. So even though it's on a unit circle, the particle, as it were, is not moving, in standard position. Standard position is we start here and go counterclockwise. This particular example, we're starting at the North Pole, as it were, and we're going clockwise, just like a clock would go, so to speak. 12 o'clock, let's say, and then it's going this way, just like a regular clock would. Okay, so that's all for that one. Okay, B, a little bit of a variation. X equals sine of t, y equals cosine t plus 1. I don't want the plus 1. Just subtract it out. So y minus 1 equals cosine t. So you can see the strategy. we're very forceful here. Force it to be sine and cosine, square both sides, and then add them up, because once I have sine squared t plus cosine squared t, I'm going to get 1. So x squared is sine squared t plus y minus 1 squared is cosine squared t. And there it is, it's equal to 1. So I have x squared plus y minus 1 squared is equal to 1, which is also a circle, but it's not centered at 0, 0. This got translated 1 unit upward. If you replace y with y minus 1, that moves 1 unit up. So the center is 0, 1. The radius is still 1. Okay, so it's like so. And which direction is increasing t? Once again, I just plug in easy numbers like 0 and pi over 2. Okay, so I'll plug in t is 0. So t is 0, x is 0. Put a 0 here. Cosine of 0 is 1. 1 plus 1 is 2. So you start at 0, 2 again. So you're up here. And then at pi over 2, you're at 1, 1. So see if I can convince you of that. Pi over 2. Sine of 90 degrees, sine of pi over 2 is 0. Cosine of pi over 2 is 1. Sorry, cosine of pi over 2 is 0. 0 plus 1 is 1. So you're at the point 1, 1. Okay, so you start at 0, 2, and you move over to a little curl on the paper here. Try to uncurl it a little bit here. Okay, so you go from 0, 0, 0, 2 to 1, 1. So again, you're going clockwise, starting at the top, at the North Pole, as it were, and you're going this direction. Okay, so this picture is exactly the same as this picture, only it's translated 1 unit up. Okay, as you can tell from here, this was x squared plus y squared equals 1, center of the origin. X squared plus parentheses y minus 1 squared equals 1. Well, that moves the whole graph 1 unit up. So imagine taking this thing and moving it up 1 unit, and it looks like that. But everything else otherwise is the same. Is that right? Okay, the next variation on the theme is part C. X equals cosine t plus 1, y equals sine t. Yeah. Okay, so same thing. I don't want that 1. Subtract it out. So subtract 1. X minus 1 equals cosine t. So same game. I square both sides here, square both sides here, and then add them up. Why? Because then you have cosine squared t plus sine squared of t, and that's going to be 1. So x minus 1 squared plus y squared is equal to cosine squared t plus sine squared t equals 1. So same game, pretty much. So my equation is x minus 1 squared plus y squared equals 1. My center is now 1, 0. I shift this graph 1 unit to the right. It ends up looking like this. And once again, where does it start? What's the direction? I plug in 0 and pi over 2, let's say. So do I always plug in 0 and pi over 2? Well, if you have something that's round or circular, that's normally a good idea. Okay. So if I plug in 0, cosine of 0 is 1. 1 plus 1 is 2. Sine of 0 is 0. So we start at 2, 0. So we're starting here this time. And then pi over 2. Cosine of pi over 2, cosine of 90 degrees is 0. 0 plus 1 is 1. Sine of pi over 2 is 1. So I go to 1, 1. Okay, so this time we're starting here, 2, 0, and we're going counterclockwise. Just like in trig in standard position, only this graph got moved over 1 unit to the right. Okay, so if you can imagine shifting this thing back over like this, this is standard position for trig, right? Where you start t equals 0 here, and this direction is considered positive by convention. So that's exactly what's happening here, except the whole circle got shoved over to the right by 1 unit. So there we go. All right, and finally, D. X equals cosine t, y equals sine t plus 1. I don't want the 1, so I subtract 1. Y minus 1 equals sine of t. So I play the same game. Square both sides here, I'll get a cosine squared t. Square both sides here, I'll get a sine squared t. Then I'll add them up. So x squared plus y minus 1 squared is cosine squared t plus sine squared t equals 1. So once again, I have x squared plus y minus 1 squared equals 1. The center is at 0, 1. Okay, and if you stop and think about it, say, well, didn't we just do that over here? X squared, look at these two. X squared plus y minus 1 squared equals 1. Yep, same graph, but we're not necessarily going the same direction. Okay, so this one, let's see, it started at the North Pole and it went clockwise. So it's the same graph, but just because it's the same graph doesn't mean the particle is moving in the same fashion. Okay, so again, I'll just plug in 0 and pi over 2, let's say. 0. Cosine of 0 is 1. Sine of 0 is 0. 0 plus 1 is 1. So we start at 1, 1, which is over here. Then I plug in pi over 2. Cosine of pi over 2, cosine of 90 degrees, 0. Sine of pi over 2, sine of 90 degrees is 1. 1 plus 1 is 2. So I go to 0, 2. So this time we're starting here and going this direction. Again, that's exactly like the unit circle, except it's 1 unit up. Okay, so yes, I have the same circle, part D as part B, but it's not traveling the same fashion. So in part B, same circle, but we're starting at the top and going this way, and going around the circle. Part D, same graph, but we're starting over here, it looks like, and we're going the other direction. We're going counterclockwise. So we're going like that, it looks like. Okay. All right, so that's that. Okay, then 17 and 19, I'm already done, folks, so we'll be done fairly rapidly, I think. So 17, kind of the same thing. I see cosine sine, sine cosine, t and radical 1 minus t squared, and negative t radical 1 minus t squared. Okay. They seem totally unrelated, but they're actually not. Believe it or not, they're very similar. So let's see if we can make heads or tails out of that one. Okay, A. X is cosine t, y is sine t. So hopefully we've seen this game often enough. We square both sides, x squared plus y squared. That'll give me cosine squared t plus sine squared t equals 1. So x squared plus y squared equals 1. That's our familiar unit circle from trig. Okay. In fact, you can tell this is how we define the unit circle. X is defined to be the cosine of the angle. Y is the sine of the angle. So this is a circle, center at the origin, radius of 1, standard position. So let's double check. Plug in 0. Cosine of 0 is 1. Sine of 0 is 0. So it starts here, just as we expect it to from trig. All right, we start here. And how about pi over 2? Cosine of pi over 2, 0. Sine of pi over 2 is 1. So we go from 1, 0 to 0, 1. That's exactly the way a particle travels on a unit circle from trig, right? So unit circle, x squared plus y squared equals 1, starting at 1, 0, going counterclockwise. That's the convention in trigonometry, right? All right, what's happening in part B? Now they have x is sine t, y is cosine t. So they basically flip these. So let's see what happens. So again, square both sides. X squared is sine squared t. Y squared is cosine squared t. So I add them up. X squared plus y squared equals sine squared t plus cosine squared t equals 1. So I have the exact same circle. It's the unit circle. But which way is this one going? So I plug in t is 0. Sine of 0 is 0. So x is 0. Cosine of 0 is 1. So this picture starts at the North Pole again, at 0, 1. then what happens when I plug in pi over 2? Sine of pi over 2, 1. Cosine of pi over 2, 0. So it goes to 1, 0. Okay, so picture 17a and 17b. Same circle, but 17a travels exactly as we normally expect for the unit circle. Namely, we start here by convention and we go counterclockwise. For B, we're starting up the North Pole and we're going clockwise. We're going this way. Okay. All right, so again, you could have the same graph, exact same picture, but you're not going the same direction and you don't necessarily have the same starting point. Okay, you can't tell sometimes ahead of time. All right, now, C and D, they don't have any trig function, and yet I claim it's going to be very much related to what we have over here. Okay, so let's see. X equals t, y equals square root of 1 minus t squared was the given question. Now, I'm inserting something extra. From the get-go, y has to be greater than or equal to 0. Do you agree? If you have an equation like that, y cannot be negative. So y is greater than or equal to 0. All right. Well, since t and x are equal, right? If t or x are equal, I can replace t with x. So it looks like y equals radical 1 minus x squared. Square both sides. Y squared equals 1 minus x squared. Add x squared plus y squared equals 1. So once again, I have my familiar unit circle, sort of. I don't really have it because of this restriction that we just said, right? Because y is greater than or equal to 0. I only have the bottom part. So in a unit circle, I don't have this entire circle. I only have that part. So I'm only drawing this. So there we go. All right, so direction of increasing t, about t equals 0. X is 0, y is 1. So 0, 1. When t is 1, I have x is 1, y is 0. So it's going this direction. And there we go. All right, something similar happens for D. X is negative t, y equals square root of 1 minus t squared. Okay, just like part C, y has to be greater than or equal to 0, right? We're taking a square root of something. Okay, square roots can never come out to be negative. So again, y is greater than or equal to 0. Then again, I will square both sides. Oh, I'm sorry, I got to plug in negative t first, right? X is equal to negative t, so t is negative x. So if t is negative x, if you plug that in right here, you have negative x squared is x squared. Okay? So you have the square root of 1 minus x squared is y. Same algebra, x squared plus y squared equals 1. Okay? So one more time. Oh, I know, you could square both sides here. X squared equals t squared. I see what happens here. If you square both sides, x squared equals t squared. So I get radical 1 minus x squared. Square both sides, get y squared equals 1 minus x squared. The algebra is exactly the same as this. So x squared plus y squared equals 1. But again, I only have the top half. But this time, the arrows are going this way. So if I plug in 0, x is 0, y is 1. But if I plug in x is 1, if I plug in t as 1, then x is negative 1. That's over here. And y is 0. So this time the particle is going backwards from what it was with part C. It's going right to left. And again, I only have the top part because the original equation had this and this, same thing. Right? You can tell from here and here, y is not allowed to be negative. So I do not have the entire circle for C and D. I only have the top part of the circle. Okay. So there we go. All right, folks, number 19, and then I'm done. So give me a few minutes to do 19. Then I'll open up to questions, and if there are no questions, we're finished, folks. So 19, there's no trig. They've got t and ln t, e to the t, t squared, and 2 ln t, and 1 over t, negative ln t. So let's see what's happening. Okay, x equals t, y equals natural log of t. Well, if x and t are the same, replace this with x, y equals natural log of x. So there's natural log of x. And let's see, when x increases, when t increases, x obviously increases, so it is going this direction. And likewise, when t increases, y increases, y is getting bigger and bigger, so it's going like this. Okay, B, x equals e to the t, y equals t. And a side note, x has to be greater than 0 because we already know that exponential functions can never be negative, right? Okay, this time y and t are the same, right? So if y and t are the same, I can change this t right up here to y. So x equals e to the y. Let me take the natural log of both sides. ln, ln e cancels out. So y equals natural log of x. So believe it or not, it's the exact same graph as this. Y equals natural log of x. Looks like that. And let's see, when t increases, y increases. That means it's going up. So again, it looks like this. So even though these two have separate parametric equations, they both yield the exact same graph. Y equals natural log of x, y equals natural log of x. Same thing. Okay, C, x equals t squared, y equals 2 natural log of t. That looks completely different than all these, and yet it's not. Let me show you why. Okay, we have a property of logs that says if you have a coefficient in front of natural log of t, I can make that 2 climb back up here by the t. So y equals natural log of t squared, right? So in other words, these two are equal. 2 natural log of t and natural log of t squared, right? Remember the 2 can go back up, or you could say take this 2 down, same thing. Now, x is equal to t squared, which means in any mathematical sentence for this particular problem, anytime I see a t squared, namely here, I'm allowed to change it to x. So y equals natural log of x. There it is. Same graph. Same graph, exact same graph. So I'm not bothering to graph it again. I already did it. Okay. D has pretty much the same theme. It looks completely different than the others. X equals 1 over t, y equals negative natural log of t. It's actually the same thing. Okay, negative natural log of t. Pretend it's like negative 1. If you say negative x is like negative 1 times x, right? So negative ln t is negative 1 times ln t. Well, play the same trick as over here. The negative 1 climbs up. Y equals natural log t to the negative 1. And what is t to the negative 1? 1 over t. And yeah, we know t is greater than 0, and that means x is also greater than 0, because you can only take the natural log of positive stuff. All right, so negative ln t, negative 1 ln t. Negative 1 climbs up, so we have natural log t to the negative 1, and t to the negative 1 is 1 over t. So I have natural log of 1 over t is the same thing as this. But x is equal to 1 over t. So that means anytime I see 1 over t, I can change it to x. So again, y equals natural log of x. So in a nutshell, they're all the same. This, and this all yield the exact same graph. Y equals natural log of x. So they all pretty much look like that. So I didn't bother to graph C and D. It's the same graph. You know, that's the same. That's the same. They're all pretty much the same for this one. Okay. I'm finished, folks. Okay, I did see something come into the chat. So now I'll let you ask questions, and when that stops, we're finished, folks. Okay, so let me check the chat. It's a little bit difficult, but I think I figured out how to do that. Okay. For problem 18, how do we create the table? Let's see. So somebody asked about problem 18. You weren't asked to do 18, so let me see if it's worth doing that. No. Okay. 17, how do we create the table? Whenever I see sine and cosine, I would normally just plug in 0, pi over 2, stuff like that. For C and D, I just plugged in easy stuff like 0 and 1. That's pretty much all I did for that. So since 17, there was trig involved. And a lot of times they want us to start with 0 anyway. If possible, sketch the graph showing where t is 0. Okay, I mean, a lot of science experiments, right? When you do experiments in the science laboratory, and you say go, right? Okay, the experiment runs. At the start, t is 0 normally. We don't start at 7 or -5 or something like that. We normally start at t equals 0. And then I thought convenient was pi over 2. That's why I just made from the table 0 and pi over 2. 0 and pi over 2. Okay. Now, in these cases, where there was no trig, I just did 0 and 1, and that was enough. Right, so I plugged in 0 and 1, that told me, okay, now the graph is going whatever direction. Right, so for 17C, if I plugged in 0 and 1, I got this point and this point. Okay, so I know it's going this way. And for D, it was going the other way when I plugged in 0 and 1. And it goes like so. Okay. All right. Okay, any other questions, folks? Otherwise, we're finished. I don't see anything. I don't hear anything. Okay, folks, so your assignment for tomorrow is to come up with any questions in chapter 6. So you can ask me any stuff from the parabolas, ellipses, and hyperbolas, and parametric equations. Okay. And then Thursday is the test, and your quote-unquote homework for Friday is ask me stuff from previous exams, if you want to review for the final exam, which is on Monday. Okay. All right, that'll do it for today, folks. So everybody have a good day. We'll see you tomorrow. Okay, bye, everyone.